Hello, Math 102 students. In this video, we want to discuss two concepts, logical equivalences and rules of inference. First, let's talk about logical equivalence. So we have this definition that it says, we say P is logically equivalent to Q if and only if P if and only if Q is a tautology. In this case, when is logically equivalent to Q, we write P, it's equivalent to Q. That's the most standard notation for logical equivalence, but you can also, other notations are also commonly used, like writing P if and only if Q, and or even P equals Q, and there are some more. But this is the most standard one. Uh, Before continuing to the examples, let me emphasize that if you want to be very precise in this one arrow implication or the biconditional, it's inside propositional logic and its operation in propositional logic. And in this double arrow one, it's a higher level thing. So we are talking about two propositions are logically equivalent. This statement itself is not inside the propositional logic. So that's why we use another notation for implication or biconditional. Okay, let's do the first example. We have a new operator which is defined by this truth table. It's given by this truth table. This operator takes three propositions and it assigns a truth value to it. According to this table, I want to write down a proposition using PQR and the operators that I already know, not, or, and, which is logically equivalent to this. I want to do that. At first, you may think that it's uh, really hard to come up with an expression or a statement or proposition that is equivalent to this. But actually, there is a very straightforward and mechanical solution to these kind of questions. And that's the idea that, so if, let's say, all the column was false and only this was true, then I could easily write a statement for that. What is the statement in terms of PQR and this not and or, which is only and only true in this row? What is this row? This is the row that P is true, Q is false, and R is true. So the statement that I'm looking for that is only true on this row, it is P and not Q and R. Why? Because this, if I want to have true only in this row, then necessarily P should be true, Q should be false. In other words, not Q should be true, and R should be true. So, and this is and, not R, and R, and R should be true. So this is the only combination. Note that for and, it is true only if all of them are true. So this is only true if this combination happens, and hence it's only true at this row. I can do the same thing for this row, which is true. So I can say that the combination that it's true only on this row, it's not have P and not have Q, so not Q, and R. R is true in this case. Okay, so one of them, it's only true on this row. The other one, it's only true on this row. And these are the only two rows in this column that are true. So now how can I combine them to get an expression that is true on these two rows, but not any other row? So that's what OR does. If you combine bunch of statements using OR, then it's true if at least one of them is true. So the statement that I'm looking for is OR of these two. Let me connect them with OR. And this basically I explained that this is logically equivalent to this new operator that is defined using this column. You see that this is very mechanical and very straightforward strategy that can work on anything. Let me give you one comment. Here I had only two truths. That's why the expression that I found, it has two parentheses and then or of them. What about if, for example, I had six truths and two falses? Then if I want to apply this strategy, then I need to write six of these things and then connect them with or. So maybe a shorter way is to, instead of considering this, if you have many truths but few falses, consider actually negation of this. Then you have fewer truths than falses. And write a statement for that negation. And then when you found a statement which is logically equivalent to negation of what you want, then negate everything, and the new statement that is negation of that is the answer. Uh, so while this is can be still be used, but you get a longer statement if you have very large number of truths but very few number of falses. So you can just in that case, if you want to make it shorter, you can consider negation of the statement, then false and truths will be swapped and you will have much fewer truths than falses. Then write a statement for that negation and then add a negation to the whole thing. So that's also a trick that you can use. Let's do other examples. We want to see if the two statements that we have are logically equivalent or not using truth table. So this and this, P implies Q and Q implies P. So if I do the truth table for P implies Q, I know that P implies Q is only false if P is true and Q is false. P true, Q false. That's the only row that this is false. The other rows, it's true. How about this? Q implies P. Let me write down the solutions in red. So So Q implies P. Q implies P. It's only false if this is true, but this is false. Q true, but P false. That's this row. So it's false here. Everywhere else, it's true. Now, I look at this column and this column. Are they the same, exactly identical? No. This is false here, but it's true in the other one. Or this is false here, the other one is true. So they are not identical, so they are not logically equivalent. If you like to use directly the definition that something is logically equivalent if and only if Q, it's tautology, then you may want to add another column, which is this. Q implies P. This, if and only if this. And see what happens to this column. This is exactly the has valued which looks at these two, and if they are identical, it's true. If it's not identical, it's false. So it's true here. They are not identical here. It's false here. It's false here, and it's true here. And you see that since not all the column is true, it's not tautology. Hence, these are not logically equivalent. That's fine if you don't do that this last step, and just after this explain that these columns, these two columns are not identical, hence they are not logically equivalent. So that's also fine. So this is the answer is no, they are not logically equivalent. But let's now do this one. So let me write P implies Q, which is basically the same. It's only true if P is true, and only false if P is true and Q is false. That's this row. And the others are true. Then I need not P. Let me write not P. Not P, it's false, false, true, true. I flip the values in this. And then not P or Q. So it's or of these two columns. And or it's only false. It's none of them is true, or both of them false. So I look at these and these. The only row that both of them are false is the second row. This and this. So at that place, this is false, and the other rows, it's true. Now I wanted to see if these two are logically equivalent or not. Then look at this column and this column. They are exactly identical. These columns are identical. So basically what I proved is P implies Q. It's equivalent to not P or Q. I proved that these two are logically equivalent. Okay, that's two very simple examples using truth table. Any example with truth table, it's very straightforward. So now let's look at bunch of equivalent logical equivalences that you need to understand them, memorize them, or mostly understand them. And then when you can use them without referring to the truth table. So if you want to prove any of them, you can do a truth table and prove it. Then you have this equivalence, you proved it once, and then you use it again and again. Some of them are very straightforward. You can even get mentally. So for example, P and not P. So out of P and not P, exactly one of them is true. One of them is false. And is only true if both of them is true. So this never happens. So it's always false. Something that is always false is called contradiction. So another notation for contradiction is this. So writing F or this, it doesn't matter. Always false or contradiction. Let's do one more. Let's I don't know, this one. So I have an or of two things, P and a statement which is always true. Or is true if both of them is true, but this is already true. If at least one of them is true, but this is already true. So this or is already true. So as you see, or of true with something else is true. Or let's say, for example, this one. Now I have or and a false. Or is true if at least one of them is true. This is not true. So if it wants to be true, the or, this one should be true. So it is equivalent to just P. These ones, don't memorize them as the formula. Memorize them as the property of operators. So the first two, it's that and or are commutative. So P and Q, it's equivalent to Q and P. P or Q, it's equivalent to Q or P. And associativity, so P and Q and something else, it's equivalent to P and of the other two. So basically combining these commutativity and associativity of and or, it mean you can conclude that actually the or, when you have only ands, many ands, but just ands, the order of terms and how you parenthesize them is that it doesn't matter. The same for or. If it's purely ands or it's purely ors. Actually, I use this here implicitly. When I wrote this, I didn't put parentheses like this or this, and I just said this is and of three things. Actually, in this, I'm using the way that I'm writing it. If you put parentheses, then you are not using anything. But if I write it like this, actually, I'm using commutativity and associativity of and, hence I don't need for bunch of ands to put parentheses. Okay, let's continue on that list. These ones, again, don't memorize them as a formula, memorize them as a property. It's distributivity of and on or, and also distributivity of or on and. What was distributivity? You have seen distributivity before in even higher school. Let's say, for example, multiplication is distributive on on addition for real numbers. For example, when you have 3 times 2 plus 5, you can write this as 3 times 2 plus 3 times 5. That's exactly what we are doing. And will distribute on or, and also or will distribute on and. So if you have P and Q or R, then you can do P and Q or P and R. That's how I'm distributing. The same for or. If you have P or this, then you have P or Q and P or R. In this, from left to right, it's like I'm distributing. From right to left, it looks like I'm factoring. It's like I have these common things and I factor out. Okay, again, don't memorize this. Memorize this property and what is distributivity in general. Okay, then we have some other ones about negation. Double negation, it's equivalent to the original proposition. De Morgan's law, it's about how the negation acts on and or. So negation applied to and, basically you distribute negation, but you switch the and to or. And if it's or, you switch it to and. If it's or, you switch it to and. You distribute negation, and then you switch the operator in the middle. That's called De Morgan's law. And we have a bunch of equivalences for implication. One of them I already proved. This one, that's the one that I proved here. I proved that these are logically equivalent in this example. So P implies Q, it's logically equivalent to not P or Q. This you need to memorize. It's very used a lot, and you need to memorize it. This one also you need to memorize or understand what's contrapositive. Contrapositive of an implication, it's basically swapping them and negating them. So it's not Q implies not P. And that's equivalent contrapositive. It's equivalent to the original implication. You use this if you ever took like calculus and other courses in other part of the math. For example, in first calculus course, we say that a function differentiability implies continuity. But sometimes we say that, oh, this function is not continuous, hence it's not differentiable. Actually, this is contrapositive that we are using. If differentiable implies continuity, then not continuous implies not differentiable. Okay, the last one is biconditional. You can make this list larger, but these are like the most useful one. Biconditional, it's basically saying that we have this implication and also this implication. P implies Q and Q implies P. Now let's do examples that not use truth table and use these logical equivalences to prove something is logically equivalent to something else. Okay, then let me show you the example. I want to prove that these and these are logically equivalent, but not using truth table, using these equivalence rules that I have. So let's do it. P implies, I start with one of them. It's better, I think, to start with the larger one or more complicated one. Why? Because it has more room for simplification. P implies R and Q implies R. This is logically equivalent to, what can I use? I can't use anything except this, except implication. I don't have any rule here that how implication and respect to each other, like interact with each other. So the only thing that I can do is for these two, I use this rule. So for the first parenthesis, I can say it's not this or this, not the P or R. And then I have and. For this parenthesis, I can say it's not this or this. Now what can I use? Looking at it, I see that, oh, I have two parentheses and they have something in common. As I said, distributivity in one side is like, looks like I'm distributing. Using it backward, note that equivalences is a two-way thing. You can use this is equivalent to that and this is equivalent to that. Using it backward, it's like I'm factoring. So basically, let me use distributivity law to actually take this common thing out. So if I take that common thing out, I have this written out, and then I have this and this, not P and not Q. Okay, good. Now what can I use? If you look where do I want to reach, it's here. And if I use this rule on what I want to get, it's basically not P or Q and then or R. Compare it with this. You see that, oh, actually this part, they are the same because of De Morgan. So this suggests me next step here, I use De Morgan. This was just my uh, 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 brainstorming to decide what should I do next. So now I use De Morgan here, which is negation can be taken out. Then you need to swap the operator in between. So it becomes P or Q or R. Now I again, basically I use this step. I use this in the other way. Now I have something like this. I use that it's equivalent to the other one. So it's basically this implies this. P or Q implies R. And that's exactly the statement that I wanted to prove. I wanted to prove that this, it's logically equivalent to this, and this is the proof of it without using any truth table and using these basic properties as my steps. Let's do another question similar to this. It's a little bit longer or more complicated, but it's a good example. So let's prove without using truth table, just using logical equivalences. Let's prove that this statement is a tautology. Look, it seems that this is irrelevant. I don't want to prove two things are equivalent. I want to prove one thing is tautology. It seems that it's irrelevant to equivalences. But think about tautology. What was tautology? Tautology, it's a statement that is always true. So I want to prove that this statement is equivalent to always true statement. Basically, I want to prove this is equivalent to T. Now it's in terms of logical equivalences. So let me use my rules to prove it. Let me start with my statement. What can I do? First thing again to be used is Note that by the order of priority of order of the operators, and has higher priority than implication. So basically this statement, if you want to add extra parentheses, is this. It's not this. Okay, it's this. For clarity, let me add extra parentheses. Okay. The only thing that I can use here, it's an implication. And uh, as you see, that's why I'm saying maybe the most commonly used thing is this thing. P implies Q, it's equivalent to not P or Q. Let me again use that. So it's not this huge parenthesis or this. Not, let me copy it. This or this. Then what can I use? Then it's very natural. I have a not of a parenthesis connected with and. So it's very natural to use De Morgan and distribute this not into this. If you do that, you get this, and then I need to switch this to or. Okay, one other thing that I can use, since here it's or, and this is also or, and using associativity and commutativity of or, basically having this parenthesis is extra. I don't need that parenthesis. I can write just Q or R. And also I don't need parenthesis here because that's or, bunch of ors. Okay, not only that I use De Morgan, actually I can use another De Morgan to also distribute not on these two parentheses. You could, if you like, you could do it in one step and completely distribute not inside, basically use De Morgans twice, but let me do it step by step. So now let me use De Morgan one more time and distribute it one more time. Let me copy this, paste it, and distribute this. You get not P, and then I need to switch this to and not Q. Now I need parentheses because and ors are not mix up them. It's not commutative or associative. I need these parentheses. Uh, or if you care about the priority of operators, you may not need it, but it's always better practice to add parentheses for clarity. Now, if you distribute this, you get not P and not R, not R. Yeah. And now I use this rule. Not, it's equivalent to the original statement. Not only that, let's say we use that, then we don't have this. What is the next step even after that? I have bunch of ors, but in this parenthesis, I have Q, not R. And this is only Q, not R. Why not group the terms that have R together, group the terms that have Q together? Basically, what I'm using is distributivity and commutativity and associativity of or. So I can swap the orders and change the parentheses. So if I do that, what do I get is I get this, which is not P and not Q, then or Q. I get this. Let me pack them why I don't need for or parentheses. Let me pack them in a parenthesis for clarity. And then not or this and this, which is, and let me also use double negation rule. So it's just P and not R or R. And then let me pack these together. Now what should I do? The whole point of doing this grouping, that this has Q, bringing them beside each other, is to next step to distribute these to get not Q and Q beside each other. So let me distribute this and also distribute this. So distributivity of or on and. Let me use it. Then you get not P or Q and not Q or Q, or P or R and not R or R. Okay, that was the whole point, to have these beside each other. Now I can say something about this. Q or not Q. What is it? Or a statement is true if at least one of them is true. And at least one of these is true because they are negation of each other. So this is actually a true statement. If you like, I'm using this logical equivalence. P or not P, it's equivalent to true. So then I get not P or Q and true. Or, by the way, this was P, not R. P or R when I distribute it. P or R, and this is also true. Now what do I have? I have an and of two things, but one of them is true. So this is equivalent to the other one, basically. When you have and of true and something else, it's equivalent to the other one. Why? Because this is true if both of them is true. This is already true, so I need only P to be true. I'm using this. So basically, when you have and with true, you can drop the true. So you have not P or Q, okay? Or this one. Again, I don't know why I write R instead of P over and over. This is P or R. Okay, P or R. Now what should I use? I have or. Bunch of ors. So using associativity and commutativity of or, basically I can shuffle them and drop parentheses as I want. What do I want? Now I have not P and P. It's good to group these together. So I will use associativity and commutativity of or to write this as not P or P or Q or R. You don't need even parentheses, but I wanted to focus on this part and pack them together, so I added parentheses. So now I have again a similar situation like this, negation of a statement or that statement. This is always true. So this is equivalent to true or something else. Now think about this. I have or of two things. It's true if at least one of them is true, but one of them it's always true. So this or is always true. If you like, I'm using this rule. True or something else, it's always true. And basically, that's the proof that this it's equivalent to always true. In other words, this statement is tautology. You can do a truth table for this and see that, oh, actually the column is always true. But the goal of this question was to practice equivalence, logical equivalences that we have. Okay, great. Now, this was the first concept that we wanted to talk today. The second concept is basically half of the other concept. The concept that I said logically equivalent. Two things are logically equivalent if each of them implies the other one. Yeah. Now I want to do the one-way thing. Something logically implies something else. So we say that P, we say P logically implies Q if and only if P implies Q is a tautology. If instead of implication it was equivalence, then this needed to be tautology. It's a two-way thing. This is half of basically the previous thing. It's only one directional thing. Okay, and not the notation for it, we write, in this case, we write P double arrow implies Q. Again, this is a proposition in our propositional logic. This is a one level higher. It's a higher level thing that we are saying P logically implies Q. We have another terminology which is basically saying the same thing, and that's at the beginning of the lecture video, I said that I want to talk about logical equivalences and rule of inference. Another way to express this is using rule of inference. We say P1, Pn, Q is a valid rule of inference. That's another definition. Is a valid rule of inference if and only if basically these assumptions all together, basically and of these statements logically implies Q. If and only if P1 and all the way up to Pn logically implies Q. According to this definition, what was logically equivalent? In other words, P1 and Pn implies Q is a tautology. Okay, now let's do examples. Again, as first examples, we can just use truth table to check something is tautology or not. And hence, does P logically implies something else or not? Or is this a valid rule of inference or not? We can use truth table, one way to do it. So the question is, these two questions are the same question, written differently. They are asking the same thing. The question is, does P logically implies this? That's the same as, is this a valid rule of inference or not? Again, this being a valid rule of inference means and of this logically implies that. And I have only one thing here, so this should logically implies this to be valid rule of inference. So both of these are saying the same thing. What are they saying? Is P implies P or Q tautology or not? So let me do truth table and see if this is tautology or not. So first I need P or Q. This is only false if both of them are false, and the other cases it's true. Then P implies P or Q. Then we have this implication is only false if this is true, but this is false. P true is here, but this false. Never we have such things. So this is never false. That means this is always true. And yes, the answer for all these three questions that are equivalent, these three questions are the same question. And the answer for all of them is yes. Yes, P logically implies P or Q. This is a valid rule of inference, and this is a tautology. So the answer is yes. Basically, we found a rule of inference. Let's do another one. Let me show you something. There are like a list of logical equivalences that I showed to you. This is a list of valid rule of inferences that we have. Basically, we proved one of them. This one here, it's called addition. We proved P logically implies P or Q. This rule of inference, it's called addition. Okay, let's do some other examples. Does now the same question as before, but for and. Is it true or not? So in other words, is P implies P and Q is a tautology? So let's do the same thing. P and Q. This is only false, only true if both of them are true. So true here and then false everywhere else. And then P implies P and Q. So this is only false if this is true, but this is false. So P true, but this false. That's this true. That's false there, and the rest are true. Now, is it true that this statement is tautology? Is it true that this column is always T? No, we have at least one false. So the answer for this is no. This is not a valid rule of inference, and P logically does not imply P and Q. Okay, and let's do this other example, which is basically proving one other rule of inference in that list that I showed to you. So for this one, I need to do the truth table for P, and P implies Q. This and this implies this. The whole thing implies Q. So for this one, I should do the truth table of this. Is this tautology or not? For the other one, it's similar, but it's Q and something. Maybe I do one of them and then ask you to do the other one as a practice exercise. P and P implies Q. The whole thing implies Q. Okay, let's focus on this for now, the first one. Is this a valid rule of inference? So I already have P. I need P implies Q. This is only false if P is true and Q is false. That's here. So it's false and then true everywhere else. Then I need AND of these two. P and P implies Q. Then it's AND of these two columns. So it's only true if both of them are true. And that's the only place both of them are true. The rest are false. And then my statement P and P implies Q implies Q. Now I'm looking this column and this column. This is only false if you have false here, but true here. Where do I have false here? Sorry, you have true here, but false here. Where do I have true there in this column? That's the only place that I have true. But then Q is also true. So I never have that this is true, but this is false. So I never have that this is false. So it is always true. And hence, it is a tautology. Since this is a tautology, this is a valid rule of inference. So this is a valid one. And you can find it in this list. It's the first one. It's called modus ponens. If you have P implies Q and P, then together they implies Q. I leave it for exercise for you to try the other one. The answer should be no. This is not a valid rule of inference. And that means, for this one, that means Q and P implies Q. The whole thing implies P is not a tautology. try to do its truth table and see that it's not always T, and hence it's not tautology, hence this is not a valid rule of inference. Okay, so like logical equivalences, you can do this and find a list of valid rule of inferences, and then you understand them, or some of them memorize them, but mostly it's about understanding them. And then every time I want to use them, then use them. So these valid rules of I can just use them. I don't need to prove them every time that I want to use. They have some names that you don't need to memorize, but when I'm using them, I mention the name for clarity that you know which one I'm using. Okay, let's practice using them. So now I know how to, if you give me an implication, I know how to check if it's valid or not. Now I have a list of valid ones. Let me use them as my basic steps of my reasoning to prove some larger statements. Let me use these things now. Okay. We have two exercises about using them. First one, it's very simple. It's just basically using one of them. I want to see these two statements logically implies what? So one of the statements it says, if I study hard, I'll pass the course. And the other statement, it says that I did not pass the course. What can I conclude from these statements using those logic rule of inferences? Uh, let me, you can either write your reasoning explain in English and paragraph, but I like to write it in the propositional logic and exactly use those rules of inference. So first, let me assign a name to these two main propositions that I have. So let me call S for I study or studied hard. Let me call this statement, this proposition S. These are my atomic propositions that I'm defining. And let me also define P for I pass or passed the course. Then writing these in propositional logic, this is saying that if S, then P. And this one, it says I did not pass the course, not P. So I have these two assumptions or these two premises. And I want to conclude something from them. If I look at my rules that I have, this is exactly this one. This one. If you have P implies Q and not Q, then you can conclude not P. And the name of this rule is modest tolerance. So basically, I can say that using S, my premises or assumptions, S implies P and not P, and using modest tolerance, I can conclude that not S, I can conclude not S. And now I translate this back into English sentence. What does this mean? Because I did not pass the course, it means actually not S. I did not study hard. So The conclusion is that I did not study hard. That was very simple examples, but you can make it in next example. We have a more complicated example. This was just to make sure that you understand how to use those rules of inference. If you like, you can write your proof step by step. Actually, I like that better. I don't like writing a long paragraphs or explanation. So another way to step by step do this proof is to say I have some steps and these are the reasons for each step. Step one, I have this as my premise, as my assumption. That's the reason that I have that is a premise or its assumption. Next one, this is another premise that I have. And then from these, basically every step that I write, it's either a premise or a consequence of premises using a rule of inference or logical equivalence. So now I use steps 1 and 2, steps 1 and 2, and modus tollens. Then I can conclude not S. Modus tollens is exactly having these two, you can conclude this. And that's basically summarizing more compact way or even more clear way of this paragraph that I explained in English. So step by step, I prove this. At the end, you can translate this into English and say that this, hence, I did not study hard. Let's do a more serious example. This was like very trivial. It was just using one rule. I want to do the same thing, but now it's more complicated. I have many premises and I should use many different rules to get what I want. Okay, so let's first again translate. These are my premises and I want to prove basically this is a valid conclusion, logical conclusion. Okay, let me read my premises. If I take a day off, it is either rainy or snowy. I took either last Monday or last Wednesday off. Last week, it didn't snow at all. Last Monday was not rainy. So these are all my assumptions, my premises. I want to see what can I conclude. To better handle the situation, let me write them in propositional logic. So let me assign some names. Because I have to, for example, Monday is rainy, Wednesday is rainy, Monday is snowy. I have two versions. Instead of giving two different propositions to them, let me use the same name, but it has like a name of day in it as well. So for example, I define OX to be I take or took the day X off. That's one proposition. So I can talk about or Monday or Wednesday. And then for rainy and snowy, RX if the day X is rainy or was not rainy. The present or past is not important. And S for a snowy. The day X is or was snowy. That's all I need. Now let me translate these statements one by one in terms of these things. And the only 2 days that I care is Monday and Wednesday. So this one, the first statement, it says that if I take a day off, so O X implies either that day is rainy or that day is snowy. I have this, but I want to use it basically twice. Once for Monday, once for Wednesday. Let me write it actually twice. Oh, let me write just Monday or M and W for M for Monday, W for Wednesday. Or Monday implies Monday is rainy or Monday is snowy. And also I have another one for Wednesday. Oh, Wednesday implies Wednesday is rainy or Wednesday is snowy. So basically out of this, I can get these two propositions and as my premises, since I only care about Monday and Wednesday. Out of this, what can I say? I took either last Monday or Wednesday off. So I know that either Monday I took off or off Wednesday. That's this statement. What about this? This again, it's a general statement for all days. So I just write it twice for Wednesday and Monday. So last week it did not snow at all. It means that Monday was not snowy and also Wednesday was not snowy. So not snow s Monday and also not snow Wednesday. These two premises, I can get this. And this one, Monday was not rainy. So only not or Monday. These are all my premises that I have. What is my conclusion that I want to prove? Let me also translate this into these propositions. And then I start writing proof for it using rules of inference. So I took last Wednesday off, so O, W, and also last Wednesday was rainy, R, W. I want to prove this. Using these assumptions, I want to conclude this. Let me write down a proof for it. So steps, reasons. I write a step-by-step proof. It's up to you. If you want, you can explain in English and explain your reasoning rather than just writing a step-by-step proof. Okay, let me see. What can I use? First, the most information that I have, it's about Monday. I know that it was not snowy or rainy. So let me actually use that. Let me use these two and combine them to join them like this expression here. So I use this premise and this premise. Not R, not RM. That's a premise. The reason is it's one of my premises. Next, not SM. That's also a premise. Then I want to get, I know that two things are separately, I have two assumptions. Now I can do and of them. If you like, that's this rule of inference. Where is it? This conjunction, second last one. If you know P and Q as premises, then P and Q, it's the conclusion. So I have steps 1 and 2 and conjunction. Rule of inference that I showed you. Then I have this and this. Not RM and not SM. Then what was the whole point of this? I want to, I joined these to get something like this. But this is or, this is and. But now I can use De Morgan. De Morgan, no, recall that logical equivalence. It's even stronger than logical implication. So when you have a logical equivalence, actually it's also both side implication. So you can use in your implication also logical equivalences, but not vice versa. In the when you are proving logical equivalences, you cannot use implication. But when you are using proving implication, at the middle you can use logical equivalences. It's a stronger. It's a two-way thing. So now let me use a step 3 and De Morgan. Then you get not Rm or Sm. Okay, now I'm in good position. If I bring this beside that, then I can use a rule of inference. Let me bring this premise now. 5, it's OM implies Rm or Sm. This is premise. Now I have this and this. Look at this. This is a rule of inference that I can use. We already used it once. It's modest tollens, the second one. Using modest tollens, I can conclude that not assumption is true, not the first part. So using steps 4 and 5 and modest tollens, I can conclude not OM. Okay, good. Now what can I use? Look at my assumptions. OM, I have it here. Now let me use this. So bring this premise, which is either I took off Monday or Wednesday. OM or O Wednesday. Okay, good. This probably it's one of another rule of inference. If you have or of two things, this is the middle one, disjunctive syllogism. If you have or of two things and one of them is false, then the other one should be true. These are very intuitive. If or and or is only true if at least one of them is true. So if you know already one of them is false, then the other one should be true. So basically, you don't need to memorize them. You need to understand those rules, basically. Okay, so steps 6 and 7 and what was the name? Disjunctive syllogism. Again, you don't need to memorize these complicated names, but you need to understand them, know the rules, and use them. You can say, and one of the rule of inference. You don't need to memorize the names. But for clarity, I include the real names. Okay. Then what can I conclude? I can conclude I have or of something. One of them is not true, so the other one should be true. So I can conclude OW. Now what should I do? Look at what I'm doing. I already used this. I used this. I used this. I used this. These two are the ones that I haven't used my premises. Now I have OW. That suggests me to use this next. And this will be the only one that I have not used yet. Okay, let me continue. Use this. Now bring this premise. 9, it's OW implies RW or SW. And this is a premise. Now I can use steps 9 and 8, steps 8 and 9, and another rule of inference is the first one, modus ponens. This one, which is called modus ponens. If you have an implication and the first part of implication is true, then you have the conclusion of implication. And modus ponens. Okay, then I can conclude RW or SW. Now, let's use the only thing that we have not used yet. This is the only premise that I have not used yet. So let me use that. Not a snowy Wednesday. 11, not SW. Step 10. No, that's just premise. Then I can use these two steps like the one that I used here. When you have these two, then you can conclude you have an or, and one of them is not true. So the other one should be true. So it's this step like here, that it was disjunctive syllogism, but only, oops. It's steps 10 and 11 that I'm using. And disjunctive syllogism, it implies that I have RW. So I can conclude that Wednesday was raining. I used my old premises and basically I'm in a very good position. What I wanted to prove is this. It's that I took off on Wednesday and also Wednesday was rainy. So I have RW here and I have OW here. Basically now I can, I proved each of them separately. Now I should AND them. And this was what rule? It was conjunction. I once used it here. And you can AND them. If you look at rule of inference, it's second last one in this table. No, actually it's not second last one. Yeah, it's second last one. Oops. Sorry. Yeah, it was second last one. It is the rule that if you have P, Q, and then P and Q, this is the second last one, and it's called conjunction. So if I use steps 11 and 12, no, not 11, what was it? 8 and 12 and conjunction. Then you get OW and RW. This is a step-by-step proof of the fact that these statements logically implies this statement. That's very nice, isn't it? Okay, great. So that was a practice to you how to use a step-by-step apply rules of inference. Okay, that's basically all things that we wanted to discuss. But let me, out of these logical equivalences and rule of inferences, actually let's make some concrete methods of proofs that more or less, if you have done proofs before or you have seen them, basically you always use them without this explicit knowledge of logic that what you are doing. So let me explain the common methods of proofs to proving bunch of statements. Let's say you want to prove a theorem that it says if something then this. So you want to prove P implies Q. P logically implies Q. That's what you want to prove. Then there are different ways to do it. One way to do it is the direct proof. So to prove that, how do you do that? You take this as your premise or assumption. Then under this assumption or premise, you need to prove Q. So the direct proof of P implies Q is under assumption, under, or let's say take P as an assumption or premise, then prove Q under this assumption. This process in total, it's basically the proof of P implies Q. That's a direct proof. If you want to prove the same statement, P implies Q, but using contrapositive, what was contrapositive? The contrapositive of an implication was this. And I knew that P implies Q is logically equivalent to this. So instead of proving this, actually I can prove this. And now what is the direct proof for this contrapositive? It's assume this, then prove this. That's the basically proof by contrapositive proving this. So it's basically the same thing, but the assumptions and conclusions are different. I take not Q as my assumption, or in other words, I assume Q is false. Then I prove not P under this assumption, Many times you have seen proof by contradiction as well. What is the idea of proof by contradiction? One rule of inference which was not in that table is this. This rule of inference, it says if P implies false, always false, or in other words, P implies contradiction, always false is contradiction. So that actually logically implies not P. In other words, if you want to prove not P, then take this as your assumption, then try to get contradiction out of it. If you can do that, then you actually proved not P. So this is like proof by contradiction. So if I want to do proof by contradiction and my conclusion is P, not P, then let me just replace not P instead of P, negation. So then I have not P here and then just P here. Or if you like, not P, but that's a double negation, it's P. So basically I should do this. I should take this as my assumption or premise, and then I should get a contradiction. Then out of this process, I prove that P is true. So proving P using proof by contradiction is taking not P as your assumption and then prove or find a contradiction or get a contradiction under this assumption. Then get a contradiction under this assumption. Assume this, then get contradiction. Then you proved P. You can use proof by contradiction, not only proving this, for example, proving an implication as well. Now what should I do? If I want to use the same idea, proof by contradiction of an implication. First, if I want to prove this, the direct proof, what should I do? I should take this as my assumption. So take P, or let me just copy this statement. Take P as an assumption. Then what should I do if I want to do direct proof? Then I should prove Q. Now that I should prove Q, I use proof by contradiction. Proving something, I don't prove it. I assume not of it, and then I get contradiction. So basically, add one more assumption in my list of assumptions, and that's not Q. So basically take P and also not Q as assumptions. Then I need to get a contradiction. Then get a contradiction under these assumptions. Then basically I prove this. So you see that this logical equivalences or rule of inferences, actually it's everywhere used when you are doing a mathematical proof. Okay, I hope that you enjoyed the video. Thank you for watching, and I hope that this was very interesting topic for you. Thank you. Bye.